Chapter 15, Multiple Integrals, Section 15.1, Double Integrals over Rectangles. The double integral of f over the rectangle R is this double integral symbol over here, of fxy dA, and we set that equal to the limit of this double Riemann sum over f of x ij star yij star delta a. The points xij star and yij star are called sample points. Delta a is equal to delta x times delta y, or change in x times change in y, and that's the area of the rectangle Rij formed by the subintervals from consecutive x values and consecutive y values. So what this looks like is we take some surface and we look at kind of patches of the surface over some rectangular region. We chop up the rectangular region into tons of little tiny subrectangles, and then we look at a single sample point in each of those subrectangles, and we look at the f value of or the z value of that sample point. Then we take, so that's basically the height. So we take that f of that value times the sample point, we multiply by the area of the rectangle, so we're basically stacking up all those rectangles, and we get a three-dimensional rectangle, or aka a rectangular solid. So we do that for every single one of our sample points. We stack up all of those rectangular solids underneath our curve, and we use that to get the area underneath the curve, because as we take more and more and more of these rectangular solids, then our approximation gets smoother and smoother and smoother until it exactly equals the area, which is, our motivation for defining an integral. Actually, not really area. In this case, we're going to get volume, area in 2 dimensions, but we're in 3 dimensions now. We're stacking up rectangular solids. We're multiplying by area, so we end up with volume. Therefore, it should make sense that we define the volume to be the double integral, which we define to be the double Riemann sum with the limit. So this will be the volume of the solid that lies above the rectangle R and below the surface C equals f of xy. So as an example, how about we estimate the volume of the solid that lies above the square, the 2x2 square, and below the elliptic paraboloid? We'll divide our 2x2 square into 4 equal squares, and then choose our sample point to be the upper right corner of each of our squares. So in order to do this, how about we first draw what the squares look like? So here's our xy plane. We've got some 2x2 squares. So how about I put, here's like 1, and then here's 2. So something like this. So here's 2, 1 on y, and 2 on y. So that means that this is the point 1, 1. This is the point 2, 1. This is the point 1, 2. And this is the point 2, 2. So what I'll do is I'll call this rectangle 1, 1. I'll call this rectangle 2, 1, rectangle 1, 2, and rectangle 2, 2, corresponding to sample points in the upper right corner, because that's where I chose all of these guys. Okay, so I would like to also try to draw what the surface looks like over these rectangles, so I could try drawing what the rectangular solids look like. So how about we see if we can draw our surface. This is going to be a huge challenge. Make it curve a little bit more. So maybe something like this. Okay, and I should probably put in some axes. So here's my z-axis, and we'll cut down through. And I'll put it behind my rectangle, so I'll keep it dashed. And maybe one last dash. Something like this. Let's see. Okay, that could be my y-axis. And I need to go a little bit more over here to get my x-axis. Okay, so notice that this is the surface z equals 16 minus x squared minus 2y squared. So it intersects the z-axis at 16. Just plug in x and y equal to 0. And remember, we're only doing this over the square that's 2 by 2, so I'll just consider these guys stopping at 2. And my grid, that wasn't so good. Should be something roughly like, try to make it like roughly parallel to the y-axis. Okay, that's as good as we're going to get. So here it is. Something like this. Okay, so here are my sample points. So this grid on the bottom in the XY plane is this grid over here that I drew over there. So now let's see if we can try to project upwards to fill the volume in between. Let me try fixing this a little bit though for my sample points, because this is going to make my rectangles all messed up, my rectangular solids. So how about I go a little bit, there we go. Okay, so now I could try to go upwards maybe. Maybe a little bit too far. But something like that, yeah. And up over here. And I'll just go across now. And then up here. So I get something roughly like this. Not perfect, but that's okay. Do my next one. Over my next sample point. So it's kind of hard to see, but it's a little bit higher over there. Okay. I guess that'll do. And I need another 2 of these guys. Let's see if I can power through for 2 more. So maybe I'll try drawing this, and then that, and add some perspective to it. Wow, well, it's roughly box shaped. Not very good box, but still. Oh, I should have put this line afterwards, so we'll do it after. Because I want to do one more above. Let's see. And 2. Okay. So that's roughly what it looks like. I've got these 4 rectangular solids that fill up the volume underneath, but not, perfectly obviously. There's some gaps in between. So this is just an approximation for the volume underneath. If I wanted the actual volume, I'd have to take the limit as the number of these rectangular solids tends to infinity. Okay, so let's say that the volume is approximately the sum from I equals 1 to 2, because we're only doing up to 2 for x, and we're only doing up to 2 for y. Oops, should I just use j for my other index? And I'm doing f of xi, I just did a j of course, xi yj times delta a. Notice that delta a is just the area of any of these rectangles, and they're all 1 by 1, so delta a is 1 for all of these guys. So f of 1, 1 is my first xi, yi, because my first sample point is 1, 1. And I multiply that by the area delta A. So that'll give me this rectangular box at 1, 1, because I'll just take the area and then I multiply by the height, which is this f value, this z value. Okay, so my next sample point was at f of 1, 2, and I multiplied that by delta A, and then I multiply f of 2, 1 by delta A, and f of 2, 2 by delta A. So I get 13 times 1 plus 7 times 1. See, all I'm doing is I'm taking 1, 1 and plugging it into my function, and then I take 1, 2 and plug it into my function to get the height, and so on. So next I have 10 times 1 plus 4 times 1. So an approximation for my volume is 34. What if we wanted to just evaluate integral? Well, we kind of need some sort of trick because we really don't want to take the limit of a double Riemann sum. That sounds horrible. So let's try drawing this to see what's going on over here. It's roughly cylindrical shaped because notice this is the square root of 1 minus x squared. So if it was just 1 minus x squared without the square root, then it would be a cylinder, but this is just the top half of the cylinder. Okay, actually, no, I don't like that. I want to curve it. Something like this. Okay, that's a little better. So that's roughly cylindrical shaped. So let's say I put the z-axis over here, and this is the point 0, 0, 1, because that's when x and y are 0. Z will have to be square root of 1 is 1. And put my x-axis over here. Remember, they gave me x going between minus 1 to 1, so that means that this point over here is at 1. And they told me that y goes between minus 2 and 2, so when I put the y-axis over here, I know that this point must be 0, 2, 0, where y is 2. Okay, so it looks like I've got this half cylinder that's cut off at 2 and minus 2 over here, and at 1 and minus 1 over there. So in fact, I didn't even need this. I would have known that this is 1, 0, 0 because the radius of the cylinder is 1, but that's okay. I can interpret this as the volume underneath this surface. So that's just the volume of half of a cylinder. So I could say that the double integral over r of 1 minus x squared dA is equal to half times pi times 1 squared, because it's pi r squared, and times my height, 4, because it goes to 2 and then minus 2, so total height of 4. So half pi r squared h, because it's only half a cylinder, so that's going to be 2 pi. Similar to single variable calculus, we have a midpoint rule for double integrals, where we just take our sample points to be the midpoints, x, and we'll call those xi bar and and yj bar. So xi bar is the midpoint of the interval of 2 consecutive x values, and yi bar is the midpoint for the interval for 2 consecutive y values. So how about I try drawing this rectangular region over here, and we'll use the midpoint rule with 2 values over there, so we'll have 4 rectangles to estimate the value of this double integral. So I'll draw my rectangles, my rectangular region, and my sub-rectangles also. So I should be going from 1 to 2 for y. So I should already start my rectangles at 1 and then stop them at 2. But for x, I go from 0 to 2, so I can go all the way across. That's nice. So let's say that over here is x equals 1, over here is x equals 2, and then over here is y equals 2, y equals 1. I want 4 rectangles because I need to take 2 for m and 2 for n, so that means that the xi's go from 1 to 2, so I need 2 xi's, and the j's, the yj's go from 1 to 2, so I need 2 of those also. So I need 4 rectangles, like I said. Halfway through is halfway between 1 and 2, so this would be at 1.5 or 3 over 2. And over here, this corner is at 2, 2. So how about I just fill in now my midpoints? So the middle, the center of each of these rectangles are the sample points I want. So how about I call this rectangle 1, 1, rectangle 2, 1, rectangle 1, 2, and rectangle 2, 2, the same as I did before, even though this time the points that I choose will not be 1, 1, 2, 1, 2, 2, and 1, 2. They'll be the midpoints of these subrectangles. Okay, so I need to find x1 bar. So that's halfway between over here. So halfway between 0 and 1, so that's just half for my first middle x value. The next middle x value is just going to be x2 bar, and that'll just be 1.5 or 3 over 2. For my y's, it looks like my first y is between 1 and 1.5, or 1 and 3 over 2, so that's 5 over 4. And then my next y value for my sample point be between 3 over 2 and 2, so that's 7 over 4. Okay, I also need the area of each of these subrectangles. So it looks like they have length 1 and height half, so the area of each of these, delta A, is equal to 1/2. I think that's enough. Now I can use the midpoint rule. So my double integral over r of x minus 3y squared dA is approximately this double sum from 1 to 2 of f of xi bar yj bar delta A, and that's just going to be f of x1 bar y1 bar delta A plus f of x1 bar, I need a comma, y2 bar, that's my next sample point, delta A plus f of x2 bar y1 bar delta A plus f of x2 bar y2 bar delta A. Okay, so that's all of them. Now I'll just plug in. So I'm plugging in f of 1/2 5/4 delta A plus f of 1/2 7/4 delta A plus f of 3/2 5/4 delta A plus f of 3/2 7/4 delta A. Okay, so that ends up becoming negative 67 over 16 times 1/2 plus negative 139 over 16 times 1/2 plus negative 51 over 16 times 1/2 plus negative 123 over 16 times 1/2. Add it all up, we get negative 95 over 8, which is equal to negative 11.875. as an approximation for our integral. Suppose that f is a function of two variables that is integrable on the rectangle AB by CD. We use the notation integral from a to b of f of x y dx to mean that y is held fixed and f of x y is integrated with respect to x from x equals a to x equals b. So basically, this is like partial differentiation except backwards. So we call it partial integration. And in this case, it's with respect to x because we're pretending all these y's are constant. Okay, so integrating this function gives us an iterated integral. So we've integrated already, partial integrated. That's this guy on the inside. Oops, that's this guy on the inside. And then we integrate again, but this time with respect to y. So remember that once you integrate this with respect to x holding y fixed, then what you end up with is just a function of y. So you can integrate that normally. So you only have to really do the partial differentiation holding a thing fixed one time, because what you end up with afterwards will be just a single variable calculus integral. So as an example, how about we evaluate some iterated integrals? So first, let's integrate this guy, the inner one, with respect to y. So I'll pull that out. 1 to 2 x squared y dy. So that's equal to x squared. This is a this is a constant because we're doing with respect to y. So we just have y squared over 2. Notice we didn't do anything to the x squared because it's a constant. It's kind of like if you have 2y, then it would be 2 times y squared over 2. Now we have to evaluate that from 1 to 2, but that's with respect to y. So I'm doing it from y equals 1 to y equals 2. So I'm only plugging in the 1 and 2 into the y. So I keep x squared as x squared. So I have x squared times 2 squared over 2 minus x squared times 1 squared over 2. And that's just 3 over 2x squared. Okay, so that's my inner integral. That's my partial integration of this integral with respect to y. Now that means that when I do my iterated integral from 0 to 3 and then 1 to 2 of x squared y dy dx, I just have to integrate the thing that I just integrated, partial integrated, from 1 to 2 of x squared y dy. And I'll do that with respect to x because my function that I have now is just a function with respect to x. It's just 3 over 2x squared. Like I said, our y's have disappeared because we plugged in for them. So we just have 3 over 2 x squared dx. So that's just a regular integral from single variable calculus. We can do that pretty quick. It's just x to the third over 2. We evaluate from 0 to 3, and we just get 27 over 2. So the only new part is that inner integral has to be partially integrated, partial integrated, however you want to say it. Okay, how about we first do one with respect to x now? So same integral as before, but we just switched our order of integration. Okay, so this is just going to be the integral from 1 to 2 of the partial integral from 0 to 3 of x squared y dx with respect to y. And that's the integral from 1 to 2 of x cubed over 3 times y, because this time x squared is the variable and y is the constant. So I'll do that from x equals 0 to x equals 3, which will cause my x values to disappear, and I'll just have a function of y left. So I integrate from 1 to 2 of 9y dy, because plugging 0 is no contribution, and then 3 cubed over 3 is 9, and I just get 9 comes out, y squared over 2 as normal, evaluated from 1 to 2, and that's just 27 over 2. So this was kind of cool. It didn't matter whether I went from x to y or y to x. I still got 27 over 2. So maybe there's a theorem, and of course it's a theorem. It's Fubini's theorem. If f is continuous on the rectangle where x goes from a to b and y goes from c to d, then it turns out that these iterated integrals with respect to y and then x, and with respect to x and then y, are both equal to each other. So the order doesn't matter, which is kind of cool. But what's even cooler is that this relates our iterated integrals to our double integral. So now instead of having to do the limit of a double Riemann sum, we can compute an iterated integral in either order, and we'll end up computing our double integral and getting our volume. Very convenient. Not the easiest thing to prove, though. But maybe it's a little bit easier to understand, at least, because this says that if you basically hold one of these guys constant and then slice, so let's say I'm, I don't know, slicing parallel to my y-axis, so I have all these cross sections and I stack them all up, then I get the volume. But it says that you get the same volume as if you were to stack parallel to the x-axis, which makes sense. If I'm stacking one way, it shouldn't matter. Wow, I'm so bad at drawing these things. It shouldn't matter as long as I stack according to fill up the same space underneath the curve, then I should get the same volume no matter which way I stack. But again, not so easy to prove. We're still going to use it though. So how about we evaluate this double integral, and we'll use Fubini. So we'll take the double integral over r of x minus 3y squared dA, and we will express that as an iterated integral over this rectangle. So how about we do dy dx? So that means that x will be on the outside, and x goes from 0 to 2. So I should go from 0 to 2, and then I should go from 1 to 2 for the y, and I'll be integrating x minus 3y squared dy dx. Y is on the inside, and x is on the outside. So I'll end up with a function of x. So the integral from 0 to 2, let's see, if I integrate x with respect to y, that's just a constant, so I just get x times y, and then 3y squared becomes y cubed. And I will evaluate that from y equals 1 to y equals 2 dx. Notice I'm writing the y equals to stress that I'm plugging in for the y variable, not the x variable. We have to be careful which variable we plug in for now. So this is the integral from 0 to 2 of x minus 7 dx after you plug in 2 and 1 and do your subtraction game. So this is just a single variable calculus integral. It's easy to do. It's x squared over 2 minus 7x from 0 to 2, and that's minus 12. I didn't write x equals 0 to 2 at the end because it's obvious I only have x left. All right, way easier than having to try to figure out some other way, like the limit of a double Riemann sum. How about this double integral over this rectangle? So again, let's use Fubini. So we have the double integral over r of y times the sine of xy dA, and that's the integral. Let's see, how about we put, well, we have to be careful about our order here. If I do y first, like in the previous problem, then I have a function of y and a function of y, and I have a product of those. So I'd have to do integration by parts, which sounds nasty. But if I do x first, then this is a constant times a function of x. So I just have one function of x. So it seems like I should do x on the inside and y on the outside. So y goes from 0 to pi. So I'll put that on the outside. x goes from 1 to 2. So put that in the inside so that I can do x first and not have to do integration by parts. So I have dx dy when I use Fubini to convert my double integral into an iterated integral. So we always want to choose the most convenient iteration. So this is the integral from 0 to pi of minus cosine xy. So that's super awesome. Notice if you were to take the partial derivative of this, then with respect to x, the y hops out, and derivative of cosine is minus sine, so the minus cancels. So yeah, this is good. And I'll go from x equals 1 to x equals 2, and with respect to y now. So plugging in x equals 1 and x equals 2 leaves me with the integral from 0 to pi of minus cosine 2y plus cosine y dy. And then this is a regular single variable calculus integral. It's pretty easy to do. So that's minus 1/2 sine 2y plus sine y from 0 to pi, and that's just 0. Okay, so let's revisit this problem. This is the elliptic paraboloid that we drew some rectangular solids underneath in example 1. We approximated the volume underneath this thing, but using Fubini we can actually calculate it exactly. So we can say the volume is this double integral over r of 16 minus x squared minus 2y squared, because I want to solve for z. I need my dA also. So I can do this as an iterated integral. It was bounded by planes x equals 2 and y equals 2. So that means my squares are just 2 by 2 again. They both go from 0 to 2, so it doesn't matter which one I write first. So I can just write 16 minus x squared minus 2y squared, and how about we just go from x and then y. So it looks like I should have the integral from 0 to 2 of 16x minus 1/3 x cubed minus 2y squared x by integrating with respect to x, where y is held constant, and I'll evaluate from x equals 0 to x equals 2. So that's the integral from 0 to 2 of 88 over 3 minus 4 y squared dy, which is 88 over 3y minus 4 over 3y cubed from 0 to 2, which is 48. So another useful theorem is that if we have a double integral, then we can express it as two single variable calculus integrals multiplied by each other, provided that we can separate g of x and h of y. So that means that if we have a function of x and y, but we can separate those functions into that function into a function of x and a function of y, then we can separate the integrals. And we don't even have to do partial integration. We can just do two single variable calculus integrals, one with respect to x and one with respect to y. So to prove this, we use Fubini's theorem. So we express the double integral as an iterated integral, first with respect to x and then with respect to y, and then in the inner integral, y is constant. So h of y is a constant. So that means that we can pull that constant out of the integral entirely. So if we're pulling the constant out of the integral entirely, then that means that we can then pull this entire thing out, because it's also a constant, and now, with respect to y, because this is just some function of x. So when we pull this out, we just are left with this function over here, this integral times this integral that we pulled out. So we take advantage of the fact that partial integration means treating functions as constants. Because we can separate the functions into x and y, we can factor out the function with respect to y as constant, and then we can factor out the entire integral with respect to x as constant. So it's kind of cool. As an example, how about we take advantage of that and the fact that this function is already written separately. Sine of x and cosine y are two separate functions multiplied together. So we can say that the double integral over r of sine of x cosine of y dA is equal to the integral from 0 to pi over 2 of sine of x dx times the integral from 0 to pi over 2 of cosine y dy. And we just evaluate each of those integrals separately as we're used to in single variable calculus, and we get minus cosine x from 0 to pi over 2 times sine y from 0 to pi over 2. So this guy's 1, this guy's 1, so we just get 1 times 1, which is 1. Handy. Next up, we define the average value of a function pretty much the same way as we do for one variable, except that instead of dividing by b minus a, that was the length of an interval, we're integrating over rectangles. So they don't just have length, they have areas. So we have to divide by the area of the rectangle, and we get the average value. So as an example, let's take a look at this contour map. It shows the snowfall in inches that fell in the state of Colorado on December 20th and December 21st, 2006. The state is in the shape of a rectangle that measures 388 miles west to east and 276 miles south to north. We'll use the contour map to estimate the average snowfall for the entire state of Colorado on those days. So how about we put the origin in this corner over here? So that means that x goes up until 388, and y goes up until 276. So I can write that x is between 0 and 388, and y is between 0 and 276. Then I need the average value of my function, and as we said, that's 1 over the area of this rectangle times the double integral over r of f of xy dA. Notice the area of this rectangle is the 388 miles west to east times the 276 miles south to north, so that's 388 times 276. Okay, how about we break this up into rectangles, subrectangles, and use our midpoint rule. So how about we do a 4x4, so we'll do 16 of these guys. So I could do, I don't know, I'll cut it in half first, and then I'll cut it in half again, and then I'll cut it in half again. So something like this, roughly. And I've got to cut it in half the other way now. And in half this way. One more time. Okay, not my worst thing. So I want the midpoints, so I'll go in the center, like over here, 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 here. Keep going in the center of each of these guys. And it's not perfect, but it's an approximation anyway. Okay, now that I've got all that drawn out, how about I get the area of each of these subrectangles? So notice that delta A is 1/16 because I did 16 equal size rectangles of the entire rectangle area AR, so that's 388 times 276, which is 6693 square miles. Okay, so I'm gonna approximate my double integral, which I'll use to find the average value, using the midpoint rule, as the double sum where I equals 1 goes up to 4 and j starts at 1 and goes up to 4 because x goes from 1 to 4 and y goes, well, the index for x goes from 1 to 4 because I'm doing 4 different x values and 4 different y values. So I'll do the midpoint, xi bar, yj bar, delta a, and I'll just plug in, estimating that, for example, for x1 bar, x1 bar and y1 bar, those are both over here where our z value or f value is 0. So I could say that my first f value, I'll factor out the delta a, is 0. And then my next midpoint, it's like roughly 15 or so. So I'll say it's 15. And then I'll say this one's 8. And then I'll say the next one is 7 because it's inside over here. And then I'll start over and I'll say I'll go to 2 and then 25, 18.5, 11, 4.5, 28, 17, 13.5, don't look at the decimal K out, 12, 15, 17.5, and 13. So 16 different midpoints. So we add all that up and we get 6693 times 207 because I needed to multiply by my delta A. Okay, cool. So my average value of this function is 6693 times 207 over 388 times 276 because I just took my integral and I'm dividing by the area, and that's about 12.9. So we could say that the average snowfall for the entire state of Colorado in those days was about 13 inches.